You ever download a new app all excited and it's just full of bugs? Or you hear about some huge tech project that's years late and millions of dollars over budget? Yeah, it happens all the time. And that's because building software, really good software, is one of the most complicated things humans do. So today, let's pull back the curtain and figure out why.
I mean, it's a feeling we all know, right? From a game on your phone that keeps crashing to these massive corporate systems that just don't work. And look, it's not just bad luck or a couple of sloppy coders. There's a really deep, fundamental reason this happens. It's a problem that has been bugging the industry for decades. So to really get to the bottom of this, we're going to walk through 5 key ideas. We'll kick things off with something called the software crisis. Then we'll dive into the real bottleneck, which, surprise, is our own brains. After that, we'll see how engineers figured out how to tame all that complexity, what their blueprints look like, and finally, we'll understand the huge shift in thinking that turned coding from an art form into a real engineering discipline. All right, let's jump in the time machine. In the early days of computers, making software was kind of like the Wild West. The main strategy was basically build and fix. You'd write some code, see if it worked, and if it broke, well, you'd fix it. Sounds simple enough, right? And for small, simple projects, it kind of worked. But as software got more and more ambitious, this whole approach started to fall apart big time. As programs got more complex, this build and fix thing became a recipe for disaster. You'd see the same problems over and over. Projects were constantly late, they were wildly over budget, and even when they finally shipped, they often didn't even do what the users needed them to do. And the code itself? A total tangled mess, an absolute nightmare to maintain or update. This wasn't just a few bad projects. People started calling it the software crisis. And this isn't just a feeling people had. Check out these numbers from the Slandish group. They're legendary in the software world for a reason. That huge blue slice, that's nearly half of all projects, 49%, that were delayed or over budget. But what's even crazier is that 23% slice. Almost a quarter of all software projects were just canceled, scrapped entirely. That leaves only about 28% that could actually be called a success. That's a massive flashing red light that something was fundamentally broken. So what was causing all this chaos? Was it the computers? The programming languages? Nope. The real problem, the ultimate bottleneck, turned out to be something a lot closer to home. It's our own brains. Okay, let's try a quick thought experiment. Right now, no writing anything down. How many separate, totally unrelated things can you hold in your working memory at the same time? Could be numbers, words, ideas. Just try to juggle a few in your head. Got your number? For most of us, the answer is 7. That's it. Kind of surprising how small that number is, isn't it? But that number, it represents a hard limit on our ability to think. This whole idea comes from this super famous paper from 1956 by a psychologist named George Miller. He called it the magical number 7 plus or minus 2. What he found is that our short-term memory, you can think of it like our brain's RAM, can only really handle about 7 chunks of information at once. And by the way, this is why phone numbers were originally 7 digits long. Any more than that, and we just start dropping things. Okay, so what in the world does this have to do with code? Well, everything. Think about it. A software program is just this web of interconnected parts, variables, functions, logic. For a tiny program, a developer can keep all those pieces in their head. But as the program gets bigger, the number of things you have to track just explodes. It completely overwhelms that magical number 7. The mental effort to just understand what's going on grows exponentially. Our brains literally can't keep up. And that is the absolute core reason why build and fix was doomed to fail for anything complex. So, if our brains are the weak link here, how on earth do we build these incredibly complex things like, operating systems or the entire global financial network? Well, the answer is we don't rely on our memory. We use the principles of engineering to systematically tackle and tame that complexity. And this whole engineering approach really boils down to 2 incredibly powerful ideas: abstraction and decomposition. Abstraction is all about hiding the messy details. Like when you press the gas pedal in your car, you're not thinking about the fuel injectors or the spark plugs. You just know, press this, car goes faster. That's abstraction. And then there's decomposition. This is the classic divide and conquer. You take a huge, terrifying problem and you break it down into smaller, bite-sized pieces that you can actually solve one at a time. And these 2 ideas, they're right at the heart of the official definition of software engineering. Look at those keywords: systematic, disciplined, quantifiable. This is all about taking software development from being this intuitive, almost artistic process into a rigorous discipline that can get you predictable, reliable results. Here's the best way to think about it. You could probably build a little shed in your backyard with a build and fix approach. You'll grab some wood, nail it together, make a few mistakes, but you'll get it done. But you would never, ever try to build a skyscraper that way. No way. For that, you need blueprints, you need structural engineers, you need a detailed plan for every single step. Complex software is exactly the same. It's a skyscraper, not a shed. You need a blueprint. So what do these blueprints for software actually look like? Well, let's get into it. Let's see how engineers put these ideas into practice with smart design and really thorough testing. So at the very core of good software design, you have two main goals: high cohesion and low coupling. High cohesion means that every piece of your program has one job, and it does that one job really well. Think of a Swiss Army knife. Each tool, the blade, the can opener, the screwdriver, it does one specific thing. That's high cohesion. Low coupling means that all these different pieces are as independent as possible. So if you decide to sharpen the blade on that Swiss Army knife, it doesn't accidentally break the corkscrew. That's how you build things that don't fall apart when you change one little piece. Now, the exact opposite of this elegant design is something programmers have a great name for: spaghetti code. And yeah, it is exactly what it sounds like. It's just a tangled, messy, impossible to understand mess of code where everything is connected to everything else. Trying to follow the logic is like pulling one noodle out of a giant bowl of spaghetti and trying to see where it goes. It's an absolute recipe for disaster. A real engineering process also means you have to be serious about testing. There are two main flavors here. You've got black box testing. This is where you act like a user. You don't care how it works on the inside, you just care if it does what it's supposed to do. This answers the big question: are we building the right product? Then you have white box testing. This is where you pop open the hood and you look at the engine. You're checking all the internal logic, all the pathways, to make sure the code itself is solid. This answers the other big question: are we building the product right? And you absolutely need both to build great software. So when you put this all together, what you're really seeing is this profound transformation in how we create software. It's a journey from being this kind of solo artist's craft to a collaborative, scientific discipline. And you can literally see this evolution over time. Back in the 50s, it was all about that build and fix, just gut instinct. Then in the 60s, people started fighting back against spaghetti code with things like flowcharts to add some structure. In the 70s, the focus shifted to the data, with the realization that if you organize your data well, the code becomes simpler. And then in the 80s, we got object-oriented design, which let us model the real world right in our code. Every single step along this path was a move toward more structure, more discipline, and better ways of taming that complexity. So, if you take one thing away from all of this, let it be this: the secret to building amazing software isn't finding some lone genius programmer who can hold an entire system in their head. It's about creating a system of engineering principles that lets teams of normal people work together to build truly extraordinary things. It's that shift from individual brilliance to collaborative discipline. That's the whole game. And that, of course, leaves us with one final huge question. Our world runs on software that is getting more and more complex every single day. We've made this incredible journey from chaos to code, from an art to an engineering discipline. But the challenges are only getting bigger. So what's next? What's going to be the next great leap forward in software engineering that lets us build the incredible, mind-boggling systems of tomorrow?